All right, welcome back to Chapter 9, or Topic 9. We are in the last section, Section 4, which is stoichiometry. Now, stoichiometry is definitely a big topic. It's it's basically a huge chunk of chemistry. And so this is going to be spread out probably into a few videos, probably one video per example problem. So bear that in mind. But let's go ahead and get started. So first of all, let's talk about what stoichiometry is, and let's try to unpack that really meaty, crazy, scary word. So stoichiometry is simply a quantitative analysis of a chemical reaction. You're probably thinking that's not so simple. But really all it is it's crunching the numbers behind a chemical reaction. Now, you have probably done the idea of stoichiometry before, okay? And I'll explain what I mean by that when I talk about what stoichiometry can be used for. There are three ways we're going to use stoichiometry when we look at our chemistry examples. The first way we use it is we use stoichiometry to figure out or to determine how much product will be created from a set amount of reactants. So you've got this many reactants, you mix them together, you're like, hey, I want to know how much I can make from that. The second way is you can use stoichiometry to figure out how much reactant you would need if you wanted to create a set amount of product. So you say, okay, hey, I need 15 grams of the product, so how much reactants do I need to make that? And then finally, you can use stoichiometry to figure out how much of one reactant you need to fully react with another. So, hey, I have, 35 milliliters of reactant 1, and I want it to fully react. I don't want any leftovers, so how much of the second reactant would I need to fully react with that? Sounds kind of scientific, but really, honestly, this is just basic everyday things. It's just applied to chemistry. You've probably seen something like this if you've ever cooked anything, if you've ever done a home improvement type of project, right? You have to figure out how much materials you need for your certain product. I like to give the example of, let's say you're having a dinner party for 10, right? And your cookbook gives you a recipe that serves 2. Right? So it says, hey, these are your ingredients, and as a result of mixing these ingredients, you're going to get 2 entrees. Well, you would use stoichiometry, or the idea behind that, to figure out, okay, how many materials or reactants do I need if I want to feed my party of 10, right? Or, hey, I have this much ingredients, how many people can I feed from that? It's the same idea. That's what stoichiometry is. So we're going to look at now what are the steps of stoichiometry. There's good news and bad news. The bad news is, and it's not really bad, but there's so many ways I can ask a stoichiometry question, right? There's a gajillion types of chemical reactions out there. There's all different types of quantities, whether it's grams or milliliters, you name it. But the good news is no matter what stoichiometry problem I give you, it's always going to be the same 3 steps every single time. And sometimes you might not even need to use the same 3 steps. You might just need 2 or maybe even 1 step. So we'll look at those steps, but it's always the same process. So looking at the steps, first of all, you need to start with a balanced chemical equation. Right out the door, you can't go anywhere without that. So that's important. Once you've got your balanced chemical equation, here are your 3 mathematic or calculator steps. Number 1, whatever the quantities that the problem gives you, get that converted into moles right away. Depending on what you're given will depend on how you're going to get that converted to moles. So we're going to have to probably do a little molar conversion review. We did this back in topic 2. So hopefully you kind of remember that, but we're going to review how to do that when we're going through our problems. But depending on what you're looking at, if you're looking at a solid, we're going to use molar mass. If you're looking at liquids, particularly if it gives you volume of a liquid, you would want to convert that volume into grams using density, and then you could go from grams to moles using molar mass. If it gives you an aqueous solution, which is very common, you're going to use molarity. And then if you're given gases are tricky. It depends on their temperature and pressure. At this point in the semester, the only chemical reaction we'll look at with gases are ones that are done at STP. Remember, that stands for standard temperature and pressure. So if you have a gas and it's at STP, you can use the conversion factor that any gas, doesn't matter what gas it is, at standard temperature and pressure, any gas will have a volume of 22.41 liters per 1 mole. Make sure you know that you can only use this conversion for gases. You cannot use that for liquids. Okay. So that's the first step. Whatever they give you, get it converted to moles using your mole conversions. The second step is you're going to use the mole ratio to convert to the desired chemical. So what the chemical, the question's asking about. And then finally, most likely at this point, they don't want your final answer in moles. They want it in another unit, grams, milliliters, whatever. And so this third step is convert to the desired unit. So once again, real quickly, once you've got your balanced chemical equation, your first step, convert to moles. Second step, use mole ratio. Third step, convert to desired unit. And how you do that is you'd use the same conversion factors that are up here. And it says from step 2, really that should say step 1. It's talking about up here. Okay, so a visual way of looking at that, this is the same steps, same thing, but it's a visual way of looking at it. So if this helps you better, great, go for it. So basically, whatever the problem's giving you, whether it's mass, volume, particles, whatever, get it converted to moles. That's step number 1. Step number 2 is you want to use your mole ratio to convert to the moles of your unknown substance, whatever the problem's asking you about. So that's step 2. And then, like I said, finally, they don't want the answer probably in moles. They probably want it back into either a mass, a volume, or a particle. So that's going to be step 3. And then you just wash, rinse, and repeat. It's the same process every single time. So, without further ado, let's actually look at some examples. So, nitrogen gas and hydrogen gas react to produce ammonia. So before we actually look into any of these problems that are here, let's start out with a balanced chemical equation. And I'm going to write it up here so I have some space. So nitrogen gas, which is N2, reacts with hydrogen gas, which is H2, to produce ammonia. And hopefully you remember ammonia is NH3, okay? And that's ammonia gas. So there's our chemical equation. Let's balance it so we make sure that we've got it all set to go. There we go. So now we're ready to go. We've got the balanced equation, and now we can rock and roll with the steps. So the first question is asking how many moles of ammonia can be produced from the reaction of 3 moles of nitrogen gas with excess hydrogen gas. So what I like to do is underneath the chemical equation, I start to write things that the problem gives me. So how many moles of ammonia? So here's my ammonia right here. So I'm going to put a question mark and then moles right below it. Kind of tells me, hey, that's what I'm solving for. How many moles of ammonia can be produced from the reaction of 3.00 moles of nitrogen gas? So it's saying that's your limited amount of that reactant. And then it makes the note with excess hydrogen gas. So I put a little excess right here. That just means, hey, you've got all the hydrogen in the world. You got a bunch of it, right? So obviously, the production of ammonia is not going to be based off of hydrogen because you've got an unlimited amount of it. It's going to be based off of that nitrogen because once the nitrogen's used up, it's done. Production's done. So to figure that out, we're going to use our steps of stoichiometry. First step of stoichiometry is take what you're given, which is the 3 moles, and convert that into moles. Well, it's already in moles, right? So that's nice. We don't have to do step number 1. It's already done for us. Step number 2 is use the mole ratio to get from the compound you're in to the compound you're trying to solve for, right? So this is where I'm going to use the mole ratio. And we're going to set it up like a dimensional analysis problem. Now, it's really important. Make sure you not only write the unit, but make sure you write the substance because it's really easy to forget what substance you're in. So I have 3.00 moles of nitrogen. And this is where I'm going to convert out of moles of nitrogen, and I want to get into moles of what I'm trying to solve for, which is the ammonia. And the numbers that I put there are coming from your balanced chemical equation. So there's assumed to be oh, that was terrible. There's assumed to be a 1 right there in front of the nitrogen. So for every, that's not much better, but we're getting it. For every 1 mole of nitrogen that's reacted, 2 moles of ammonia will be produced. So I would write those numbers down here, 1 mole, 2 moles there. And so 3.00 times 2, that's going to be 6.00 moles of ammonia, NH3. And then the final step, so step 1 was to convert to moles, which was already in moles. Step 2 was to use the mole ratio, which we did here. Step 3 is convert to the desired unit. What does the problem want you to solve in? Well, it wants it in moles, right? So we actually have our answer right there. It is 6.00 moles of ammonia. Now let's look at the second problem. So the second problem, I'm going to actually erase this up here. Okay, so now we're looking at the exact same equation, but now it's saying how many moles of ammonia, so I guess I could have left that, because we're still solving for how many moles of ammonia can be produced from the reaction of 3.00 moles of hydrogen gas. Okay, so this time it's the hydrogen gas that's 3 moles, and nitrogen is what's in excess. So same thing, but this time it's the hydrogen that's limiting how much is produced. So I don't need to convert to moles because it's already in moles. Okay, so I'm going to write my 3 moles, but remember this time it's hydrogen because this is 3 moles of hydrogen that we're in. And I'm going to use my mole ratio. Okay, moles of hydrogen on the bottom, moles of NH3 on the top. The mole ratio, for every 3 moles of hydrogen reacted, 2 moles of ammonia will be produced. So for every 3 moles of hydrogen, 2 moles will be produced. 3 times 2 is 6, divided by 3 is 2. Using my correct number of sig figs, which should still be 3, 2.00 moles of ammonia will be produced. Now notice here, just because I was reacting 3 moles of nitrogen and 3 moles of hydrogen doesn't mean that they're going to both produce the same. Notice if it's 3 moles of nitrogen, I can produce 6 moles of ammonia. But if it's 3 moles of hydrogen, I can only produce 2 moles, right? And that's because the mole ratio is different, okay? That's like saying, okay, well, if I have 2 cups of flour and 2 cups of sugar, then I should be able to create the same. Not necessarily. If you're looking at a recipe that calls for, to make, let's say we're making banana bread, right? It calls for 2 cups of flour, but it only calls for half a cup of sugar, right? The ratio is different. So if I said, oh, you have 2 cups of flour and you have 2 cups of sugar, you should be able to make the same amount of banana bread from those. That's not true, right? Because the ratios are different. It's the same thing with chemistry. The ratios are different for your reactants, and so that will dictate how much product can be created. All right, we're going to cover limiting reactant here, and then we're going to finish up this problem in the next video. But I want to cover limiting reactant in this video here. So we've been talking about in the previous problem situations where, hey, you have excess of one reactant, right? You have an unlimited amount of one of the reactants. Well, that's not really realistic, right? In real life, you usually have a set amount of both ingredients or reactants or whatever you're thinking of, right? So the limiting reactant is the reactant that is going to determine or limit how much product is formed. In other words, the limiting reactant runs out first. That dictates how much product you can actually make. Let's imagine we're making sandwiches, right? So in order to make a sandwich, okay, we're making, to make one sandwich, it takes apparently 2 slices of bread and 1 slice of cheese. We're making some really basic grilled cheeses here. Delicious nonetheless, but really basic. So, okay, let's say you're in a sandwich shop and you are working behind the counter and you notice that you have 28 slices of bread and 11 slices of cheese. So you have a defined amount of both. You don't have an unlimited amount, you have a defined amount. So if you used up all of the bread. If all of the bread was used up, what's the maximum amount of sandwiches you could make? Well, 2 slices per sandwich. So that would be 14 would be the maximum amount of sandwiches you could make if you used up all the bread. But if you used up all the cheese, what's the maximum amount of sandwiches you can make? You can only make 11. So how many sandwiches do you make? Do you make 14 or do you make 11? Well, the answer is the lowest of the two. Whichever one creates the lowest amount, that's the ingredient or reactant that's going to run out first. And so in this case, the cheese is actually the limiting reactant. And then the bread would be known as the excess reactant. It's the reactant that's left over. And I could ask a question, all right, well, how many slices of bread would be left over? Well, there's several different ways to think about it, but think about this. You say, okay, well, I know I can only make 11 sandwiches, right? So how much bread does that take to make those 11 sandwiches? Well, times 2 slices per, that's 22 slices of bread that you need. You have 28 to begin with, so how many slices do you have left over? 6. So you would end up having these 11 sandwiches, but then you'd have 6 slices of bread left over. So the bread was the excess reactant. The cheese limited how much product was made. It's the same thing in chemistry, and we're going to see an example of that in the next video.